Hello and welcome back to the attic. I swore last time I was not going to order any more of these solid state relays. I was pretty disgusted with them, and I don't know, I did. So this is another 60 amp. As you can see, it's identical to the other one. Even on the back plate, the stamping numbers are exactly the same. It was from a different vendor. China Incorporated, and this one is different. This one was transformer operated, and this one is photovoltaic. You can see that little square thing there. That's a little. I couldn't scrape off the epoxy enough to see what the thing is, but it might be one of those VOM ones. So anyways, this is photovoltaic, and it is slow as molasses. Look at this. This is almost 2.6 milliseconds before it turns on. And then if we go out here till where it fully turns on, we're at 7.7 milliseconds. This is the slowest thing I've ever seen. And, you can't use it for any PWM applications. This transformer-based one was a pretty fast turn on. And the turn off, there was a little bit of a delay, about 1.2 milliseconds. But that wasn't bad. That could get you into quite a bit of PWM type of stuff if you got down to a 5 millisecond cycle time. That would be sufficient. But this is very slow. See how it turns on very slow? And this one, I went in to the FET. You can see the brown wire coming out. And I'm monitoring the FET voltage. And so right now we're at 0 volts on the FET. That was a stored image, just to make things a little faster. And I'm less than a volt right now. But watch this thing. Okay, that's 1.2 volts on the LED going in. Most LEDs turn on about 1 volt, so that's not unusual. And we're at 1 volt gate. And, if you had 200 volts on this FET or 120 volts on this FET, it would be burning up right now and it would destroy itself. So let's get up a little bit higher. Now that's 1.6 volts. And once you get over 6 volts, this is likely an IRF 4332, IRFP, excuse me. And but I think it's a fake one for 2 reasons. The on resistance a little bit higher than you expect for this, and also the breakdown voltage was 275 volts, and they specify a breakdown avalanche voltage of around 300 volts. So that's suspiciously lower. So, like I say, fakes get into everything. But once you get over 6 volts, you're pretty good. You can handle a significant amount of current. They like to be up around 10 volts, but this will finally go up to 7.5 volts. So that's about 3.6 volts on the control input. But now it's turned on, and again we go down low. And this just follows us right down. Now if you notice, you'd think that this had some kind of circuitry in it, and it does. So if there's an abrupt change, it'll turn off very quickly. This is a really fast turn off. But if it's slow, the circuitry can't tell that something's happening. So at 2.28 volts with 1.3 volts input, this thing would be burning up. So I just made this pulse generator box. You know, you can get these little pulse generators, but it would never sit flat on the counter. And if you notice, I have a switch here. One is PWM. So in PWM, it comes right out of this like it should. In IGN, it's a goes to a FET, and that imitates the points of an automobile distributor for a Sun distributor testing machine. And that's what I use this for. I build those boards. I'm into everything retro. So yeah, that's why I just wanted you to see. You know, I blew out this one by trying to feed an analog signal in. I was thinking that there would be some kind of Schmidt trigger on the input where it would turn on at a certain voltage, turn off at a certain voltage. And that's not true. It just goes into this analog region and it burns up. So, you know, don't put a stack of Zeners on this and thinking like, well, at 3 volts it turns on and I can go up to another 30 volts without damaging it. But on the way down, this thing will blow up. So, that's today's lesson.